see, what's really most important when taking a look at the Arctic is to study the Arctic sea ice volume, because while the sea ice area is an interesting stat, it really is not indicative of what's really happening in the Arctic, because what we find in the Arctic is the sea ice is getting thinner and thinner and thinner. And when something starts getting thinner and thinner and thinner, I mean, it's not, yeah, right, you don't have to be a rocket scientist to just kind of travel yourself down the graph and you can see where you're probably going to end up.
I just mentioned something here. I was looking today at what do you call it, climate reanalyzer, and I was looking at these dips that you see in the chart, the 2010, 2012, all the dips that are going down. And I wonder if, Paul, you could say something about that. I believe that, you know, at present, we're kind of, it says in biomass, which you can find on Google if anybody's interested, biomass, and you can find these graphs or go to Climate Reanalyzer and you can find all this sort of stuff.
Yeah.
But we're apparently at the moment, you know, around about the 56th ever lowest. So we don't want to give the impression that we're lower than ever at the moment, but we may indeed be the lowest ever on the 20th of September. Do you want to talk to that, Paul?
Yes, well, the first thing is that it's a bit more difficult to get the volume of the sea ice, right? Because satellites can easily measure the extent, and they can measure the area, which is where there's 100% concentration of ice, and the extent is defined as at least 15% of the region is ice. And we need to get the thickness in order to get the volume of the ice, right? You multiply the area or by the thickness to get the volume of the ice. And you can see that the trend is sharply downward from year to year. 2007 was a big surprise at that time. 2012 was an even bigger surprise. And there is some variation of the melt each year. Like the characteristics of the sea ice melt are changing. So in 2007 and in 2012, there was a lot of export of ice, for example, out of the Fram Strait. There was also a lot of surface melt, and there's a lot of melting from below the ice from the warm water. So what we're seeing now is that the ice has receded so much away from the coastlines. Even this year, it was very surprising. The ice receded away from the northern Greenland coastline. And we hadn't seen that before. So it happened actually in the winter. The winds actually blew the ice off the coastline, and then the open water froze quickly. But of course, it would be very, very thin. And we've seen this again in July. We've seen this again this summer, that the ice was pulled away. So, but this year there's very little export of ice out the Fram Strait because the ice is pulling back away from the coastlines towards the central Arctic basin, and therefore there's not ice available to really be exported. So the mechanisms of the ice melt are changing. The trend is down, and very rapidly down, and we can expect a blue ocean event, you know, very, very, very soon, within a matter of years, maybe 5 years, you know, 4 or 5 years at the most. Now, the other thing is there was a paper, a scientific paper came out just a few days ago, actually, that was talking about how the surrounding water around the ice in the Arctic Ocean is dark, it's heating up, it's absorbing a lot of sunlight, and it's salty because there's mixing, a lot of waves and mixing and so on. So it's actually quite salty, and it gets very, very hot. Now, the saltier it gets, the heavier, the more dense the water is, and the hotter it gets, the less dense it gets. So those two factors compete. And what's happening is actually the water under the ice that's remaining is fresh because the ice is melting. So, and that fresh water is lighter. So that fresh, cold, fresh water is forming a lens or a pocket underneath the sea ice down to about 50 meters. Now, the winds that are moving towards the north and cyclones, for example, are blowing that warm, salty water from the ice edges towards the ice, and it's going underneath the ice. So now, about 50 meters under that cold water lens, there's very warm, salty water. And if there's enough mixing and wave action and cyclones, that heat can go up, and it's enough to take out about 0.8 of a meter, 2.5 feet of the thickness of all of the ice that's remaining. Okay, so this is a very strong feedback that could
yeah, Paul. Yeah, if I could just come in there, Paul.
Yeah.
Because it seems like, you know, the warmth is being stored under the ice. So even when we get the minimum, which is sort of September 20th sometime or whatever, the normal minimum, this stored heat will affect the extent of, and volume of the ice going into the Arctic ice's winter, yeah?
Yeah, so what happens is you know, about this time of year, the end of, you know, beginning of September, the air temperature is starting to drop in the Arctic, and that's starting to stop the melt on the surface, but the water temperature is still fairly warm, so the ice is continuing to melt from the underside. Okay, and this will be a sort of a tug of war until eventually it gets colder in the whole. Eventually, that water will cool down as well. Right. So this is what's kind of happening right now. So it'll be interesting to see. You know, typically the ice extent minimum is about mid-September, but that can vary from plus or minus a week. I think September 9th or something may have been the earliest. September 15th is typical. You know, we've had some years where the minimum is on September 20th or something like that, but it's pretty tightly confined over that period of time.
Right. And what are we looking at now, Jennifer?
Well, I thought we'd drill down on the Arctic a little bit and take a look at the geography of the Arctic. So this is a topographical map of the Arctic Ocean and a little bit of northern Siberia there, Greenland, and kind of how the land is. So what we can see right away is there's a huge, well, you can see this red mark here that was circled as an area of emphasis, but this East Siberian Sea and the Laptev Sea here and the Chukchi Sea too, they're very flat and they're left over, they're really vestiges from the last ice age. This is an average of about 60 meters deep, and it's also an area of high methane hydrate content. There are vast methane stores that are deposited here due to the fact that it's really kind of boiled down into kind of a highly distilled, you know, whiskey, like, you know, it's a very potent energy source, actually, methane hydrate is. But in any case, it's there. And what we're starting to see now, and we're going to go through a few slides and talk about this, but what we're starting to see is that this area is emitting a great deal of heat, and that there are methane fountains kind of coming up all through here, and also in the permafrost itself. So this is the area that we're really going to be focusing on. This is the Laptev Sea, and this is actually the Lena River Delta right here. So the Lena River Delta is a very rich organic area. It's full of methane hydrates and full of all sorts of biologic material. And this is also an area of incredible methane emissions right now. And the reason that we want to talk about this is that methane is a potent greenhouse gas that when it comes out initially, it can be like 100, 125 times stronger molecule for molecule rather than carbon dioxide. So this is a map from July 1st, so like what, almost 2 months ago now, I guess it's 2 months ago. And then you can see here is where the Arctic sea ice was starting to open up around that area that we were just looking at. So you can kind of superimpose those areas. But, you know, what we're finding is that the Arctic sea ice is opening up in the Laptev Sea and the East Siberian Sea earlier and earlier, and it's thinner and thinner. And so there's going to be more heat coming up, and in fact it is, because take a look at this. This is the Lena River Delta area, and you can see this was from July 1st also, so that same time frame. And you can see that this is an area of incredible heat, as is the area right, the Beaufort Sea right here between Alaska and Siberia is an incredible area of heat as well. So, you know, heat is everywhere, and this is just another illustration. This is from Thursday, and what we can see here is that whole area, which this is all permafrost, or it should be, but it's kind of turning into perma-mush, and this is northern Siberia. And this is the Lena River Delta area right in here. So this whole area in northern Siberia, and also the islands in the Laptev Sea and the East Siberian Sea, are really starting to heat up, and it's melting stuff. So Paul, given that we've just talked about, can you speak to these areas a little bit?
Yeah, well, I mean, the big risk of the ice in the Arctic keeps it cooler, you know, because it takes a lot of energy to melt ice. So that heat energy from the sun melts the ice, and it doesn't heat up the water around the ice, right? Because it's, you know, when ice melts, it comes off the ice, the liquid coming off the ice, the water coming off the ice is at the same, you know, just slightly above the freezing temperature, right? So that cold water moves off, and it keeps it colder. But now when we have regions around the ice where there's no ice, there's dark water, seawater instead, that seawater absorbs the solar radiation and heats up. And because these continental shelves are very shallow, you know, you said like 50 to 60 meters deep, that whole water column down to the sediments can heat up, and that heat can then go into the seafloor, and especially down fractures and fissures and things, and it can penetrate quite deeply and thaw out these methane clathrate deposits, and the methane will bubble up and you know, enlarge the hole or fracture, and you know, that methane can get up into the atmosphere. It easily goes through the water column because it's not deep enough to
Indeed, and even the water column itself can get saturated. It can only absorb so much methane, and if it's only an average of 60 meters deep in general, wouldn't the water column get completely saturated with methane and not absorb as much, and it would just deposit it straight up to the atmosphere at a certain point?
Yes, I mean, that depends on if there's you know, just if there's small numbers of methane bubbles coming up to the surface, then the water column can absorb that. But if the methane release rate from the seafloor is higher, then the water column gets saturated, and most of the methane gets up into the atmosphere.
Yeah. Okay.
Can I just can you educate me here, and maybe some of the watchers and listeners? I'm a little bit confused, because I thought all around the Arctic that there wasn't very thick ice. There's hardly any thick ice left at all, and we're kind of talking now about 60 meters or something of ice around.
Oh, no, we're not talking about 60 meters of ice. We're talking about 60 meters of water.
Water.
So
yes.
the water column, the ice is actually, you won't find any ice anywhere in the Arctic that's 60 meters. The ice in the Arctic is probably 1 to 2 meters at this point. Would you agree with that?
That's why.
Yeah.
Oh, no, I apologize if I mistakenly, if I said that, but what I was mentioning, and I'll go ahead and I'll share out my screen again so you can see, because what we're talking about is that this ice right along here is only like I mean, not the ice, this water right along here is only 60 meters deep. So that means that there's just not very much water for when these methane fountains start going. It can't easily get.
Right. The bubbles only have to come up through that 50 meters or so.
Right, right. And actually what I'm showing here on my screen right now is a sea ice thickness anomaly map, I think. Mike had sent me this one. I'm not entirely sure, but it looks to me, I'm not going to try and interpret this one, and I'm not going to ask Paul to. I'm going to skip over this for the time being. Sorry, I don't declare victory on that one. But what I do want to talk about, what I'm showing here, Paul, because I know your screen is a bit small, what I'm showing here now is a classic methane emissions map. It's a global map of methane emissions going on around the world. And what I'd like to draw everybody's attention to is this magenta cover that's prevalent throughout Siberia and really throughout Asia and Europe in general. We've got high methane emissions. Paul, could you speak to us about why should there be such high methane emissions? These seem to be up around the 3,000 parts per billion in methane.
Yes, in the top left, it has a range actually, 1453 to 2350 parts per billion of methane. So what you can clearly see is that there's a variation with latitude and location of methane, and this depends on two factors. First of all, where there's methane sources, things that are producing methane, whether it be hydrates or wetlands is a big producer of it, then there'll be a larger, then you would expect the methane in the atmosphere that's measured by a satellite, the detector on the satellite shown here, to be higher in regions where the source is higher. But that's not the only factor. There's another factor, is how quickly is the methane removed from the atmosphere. So what happens is water is broken down and you get the hydroxide ion, OH minus, and OH minus is like the scavenger of the atmosphere or the cleanser of the atmosphere. It's very reactive. It reacts with the methane, breaking it down into CO2 and water. So obviously near the equator, there's lots of water, there's lots of sunlight, so there'll be lots of hydroxide, and it will react. There can be a big source of methane in wetlands at the equator, but that big source can be nulled out, if you like, by the big sink of hydroxide in that region. But
that's
now
very interesting.
Okay, but now go to the Arctic, higher latitudes, higher and higher latitudes. It's colder. There's less water vapor in the atmosphere. There's less hydroxide. And therefore, the methane will last longer in those regions and be higher if the sources are not nulled out at all. So you can see that whole magenta region where there's lots of methane produced, but there's less hydroxide to break it down. On average, methane lasts about the lifetime in the atmosphere. They say it's basically about 9, 10, 11 years, something like that. It's very short. So as long as there's if there's large bursts of methane coming from hydrates in the Arctic, then because there's less hydroxide up there, I mean, when we talk about methane lifetime, it depends on the hydroxide. So you could argue that the methane lifetime changes with latitude, right? The lifetime will be shorter at the equator because there's more hydroxide, the OH minus, and it'll be longer as you get further and further north where there's less and less hydroxide to break down the methane.
Yeah, that's fascinating. I did not realize that about the hydroxide. It makes perfect sense because you can see there's a big band of red, and that's due to the fact of the additional water vapor breaking down the methane in that hydroxide sort of equation that you just alluded to. So thanks very much for that, Paul. Now, another thing that we need to talk about, because we can see we've got, you know, a lot of heat going on in the Arctic that's been illustrated and consequent methane emissions. But we also have wave action that's battering up the edge of the ice. And this here is an illustration. This is just kind of to set people's you know, where are we now? This is Svalbard right here. This gray bit that you see right here, this is the Arctic and the Arctic sea ice. And this is some little Siberian islands over here, San Joseph Island or something like that, I think. But can you talk to us, Paul, about how when these big currents hit up against the Arctic sea ice, you know, in these storms and so forth, like say a cyclone, which is currently happening this weekend in the Arctic, right?
Yes.
How is that affecting the sea ice?
Well, the sea ice, because it's so thin, there's no multi-year ice. It's much more fractured and broken up and almost like slush. So it doesn't stick together. So we saw in 2012, in August, this massive cyclone churned through the Arctic over about 10 days, and it tore off large chunks of the ice and sent it more southward. So we're seeing there's a potential for these. There was a big cyclone up in the Arctic in about June, but of course the ice it hasn't melted as much. It was more rigid, and that cyclone didn't do as much damage as it would have done, say, now when the ice has had most of the melt season to get softer and broken up. So these cyclones, of course, they increase the wave height, as your image showed. And I mentioned they also mix the water. They'll mix the salty, warm water with the colder, fresher water. And they can, when they're breaking up the ice, they can perturb the water column underneath, and that lens of fresh water that's cold underneath the ice from the, you know, that's there from the melt water of the ice. It's mostly first year ice that's melted. So that fresh water layer, if it's churned up and mixed with the warmer water underneath that I was talking about, the higher salinity water, then that heat can be sent up to the ice, and that is enough heat to take out 0.8 meters of ice, according to the study.
Wow.
The amount of heat underneath the ice in those regions has doubled in the last 30 years, according to this study. So this is a problem. This is another, a new problem. If there's a lot of mixing that goes on when the ice is supposed to be refreezing, it'll delay the refreezing of the ice. So yeah, it's a huge feedback, which is not good for the ice.
That's right. And I believe that we have a cyclone underway in the Arctic, or at least a pretty big disturbance of some sort. This is from a couple of days ago. You can see here, just for orientation, this is sideways map, you know, a little bit. So this is Greenland. There's a big cyclone thing, some sort of bad weather disturbance happening in Greenland. Then here's Svalbard up here, right? And then there's that huge, and it's just like kicking north of Svalbard and
Yes.
hitting the sea ice. And that thing is, I mean, if it's gonna, what I saw earlier this week that really, really disturbed me was the amount of heat in the Arctic Ocean that's in these different layers, and they're striated, and the only thing saving the ice at this point is this kind of fresh and cool that the ice is with. And you know, if these things come in and they just mix it all up, that's just going to make that Arctic sea ice melt very quickly. Would you agree with that, Paul?
Yes, exactly. And I was mentioning that because the ice has moved away from the coast and so on, that there's a lot less export of ice out the Fram Strait. So, but these mechanisms, these storms and things can continue. You know, we look at the trend of the loss of sea ice over time, right? It's trending down, and suddenly, you know, the years where there's very little export of ice at the Fram Strait, you might expect that the curve, that it kind of bends upward a bit and the rate of loss decreases, but you have these other things kicking in which are maintaining the rapid rate of loss.
Right. Right. And I'd also just like to illustrate, this is a drill down of the Arctic cyclone that's currently underway in the Arctic, and you see it's like swirling above Greenland. This area just north of Greenland was the area of thickest ice, as Paul alluded to earlier in this conversation. And the area here, it's actually open water here for like the first time.
Yeah,
I mean,
yeah. Just to be
time.
fair, most scientists, if you ask them, you know, where will there where will the ice last longest in the Arctic? They would say right in that region.
Right
So
here.
they have to, yes, right where it's being pulled away from the shore. So that's incorrect, and they're all having to scramble and say, okay, well, where will the ice be? You know, now what area of the Arctic has the best chance of say having some ice? And they have to, you know, come up with a different position, right? I don't know, maybe along the, I mean, the ice is basic. It's weird. You could almost take a sailboat and sail completely around Greenland.
Well,
Like,
yeah. Yeah, I mean,
right along the coast. Yeah.
it's opened up for the first time. How about in the Canadian archipelago? Is that ice still congested in there, or is that free?
Well, see, the ice used to get congested in the Canadian archipelago when the ice was thicker. It would form, you'd get these ice bridges, if you like, or ridges.
Right.
Ice would pile up, and
Just
then it would block some
smashed
of the
together.
channels. Yeah, and then it would block some of the channels, so the ice couldn't move through the Canadian archipelago. But
Exactly.
a few years ago, we could start noticing that the ice was too thin to block up the channels. So there was a lot more loss of ice starting to occur through those narrow channels of the Canadian archipelago, and that's still continuing. So, yeah, there's no areas where the ice will be resilient in the Arctic, I'm afraid.
That's it then. I mean, there's no areas where ice will be resilient. And with all this additional heat and all these storms and all this heat coming down the rivers, all the heat coming in the Mackenzie River Delta, the Lena River Delta, all the heat being imported in through the Beaufort. I mean, the Arctic is being attacked on all sides, and you can see that even from above. It's being attacked from above. It's being attacked from below. I mean, this is scary,
it's also,
really.
Yeah, I mean, also the you know, I had a video recently talking about monsoons up in the Arctic, right? And there's people, you know, we know that the heat waves this summer were horrendous in the northern hemisphere, not all over the world, but specifically one area, you know, up in Scandinavia, northern, you know, the northernmost parts of Norway and Sweden and those places.
Right.
You know, they were getting 30, 35 degree Celsius temperatures and torrential rains, basically. It was almost like, you know, the land heats up, it pulls moisture off of the open water. That moisture gets pulled over the land, rises up, and causes rain. So it's like a monsoon, a mini monsoon, if you like, in those regions. So we've been seeing that happening. Yeah, like everything is changing, right?
Right.
Yeah,
you know,
like, can I just pop in here just to test my vocal cords? Yeah, you're totally correct, Paul. I mean, the heat that we've seen here in the United Kingdom, I've never experienced anything like it, and the same has been going on for most of Northern Europe, and that is obviously bound to be having an effect on the Arctic. And you see it right the way across the East Siberian Arctic shelf. You see this heat, it varies from day to day, from week to week, but there generally seems to be these really hot areas, abnormally, you know, temperature anomalies, should I say, right the way along, and they just continue to happen. One question I had for you, Paul, was quite a simple question, really. Why do scientists, in general, climate scientists, say that is an Arctic ice, the blue ocean event, when there's like 1.5 million square kilometers? I mean, there's either there or there isn't, you know. So, well, why do they use that figure?
Yeah, I guess they use that figure because they thought that, well, we can say less than one because there's still going to be lots of ice called fast ice, which is attached to the land. But you know what? I don't think it's going to make. I don't think it makes any difference. I think when the ice is going, and we have a blue ocean event, there won't be any ice even along the coastline.
Yeah,
you know,
well, I'd like you to say how you anticipate what you've been talking about just now, and the effect in the summer of the winds and the warm water underneath the ice. How you see that affecting the development of ice in the winter?
Okay.
You know.
Okay. So good question. So the first thing that I wanted to say was that the getting back, before we forget what I was going to add another feedback about the ice is being attacked from all sides because it's so hot and dry up north. We're getting way more fires, and these fires have actually put so much ash and smoke up into the atmosphere that smoke's been pulled into the Arctic. So this has done two things. The first thing is it blocks out sunlight, so the Arctic's being cooler than it would have been without that smoke. Okay, so that would actually cause some stalling of the ice melt. The second factor with the smoke is it has to end up depositing somewhere, and when it deposits on the ice, it makes the ice darker, right? Even if the ice refreezes up over the winter, that smoke and that ash that's in the ice makes the ice darker. So next year's melt season, it will, we don't have those fires and the ice is going to melt out more quick.
Oh my God. That is so scary because it's like a temporary dampening effect of the temperature, and it's just going to double whammy the next year when it deposits itself and the air is clear, and it's just going to go shoo.
Yes.
Oh my God. I see this ice melting down very quickly now.
So how do you
for
see
many
it?
years, now the second part of the question, what happens in the winter, okay? Most scientists still are mistakenly thinking that, the ice will always be there in the winter, right? And if you look at the energy balances and you can look at the trends right now. Winter sea ice is decreasing every year, not as fast as summer sea ice. So the trends is simply, here, I've been saying this for many years. If we have the first blue ocean event in 2020, call it, maybe it's a few years later, I think within about 2 or 3 years, okay, so the first event, it might be a couple weeks in September, or all of September has no sea ice, and then it starts forming up again. Within a few years, that the duration of no ice in the Arctic will increase, and it might be August, September, October, 3 months, and then within a few more years of that, add on another few more years, and it will be July, August, September, October, November, no ice. And you see where this is going. Eventually there's no ice year round, and I think it happens very quickly. And it's one of the main reasons it seems obvious is that there's no it's a lot easier to heat up water. Take the amount of energy that melts a kilogram of ice. You end up with a kilogram of water just above freezing. Take that same amount of energy and apply it to that water that's just above freezing, and it takes it up to 80 degrees Celsius. Now, they will be mixing, so the water won't actually reach 80 Celsius. It'll be mixing with other water, but it's a huge amount of heat, and that will take out the ice here. The ice will be gone year round, I think, within a decade of the first blue ocean.
And how do you could you make any predictions or projections as to how that will affect the global temperature?
Yes, well, yes, it will wreak havoc. If we think the jet streams are bad now and our extreme weather events are bad now, ramp them up a factor of 10 or 20. I think that of course, the big risk is that we haven't even talked about methane, about the feedbacks. So the methane, it'll start coming up in ever faster amounts, and that will cause the warming to go up even higher. And we also haven't talked about Greenland, right? Greenland ice will be the only thing left with ice. The ice on Greenland will be the only ice left in the Arctic year round.
Very
likely. But say 10 years after the first blue ocean event. So how do you think that's going to fare? When it's so much hotter year round up in the Arctic, right? And so that will greatly raise sea levels quickly. When sea levels start rising so fast, what about the floating ice shelves in Antarctic, right? They also start raising up, and they will start contributing a lot more to sea level rise as well. So we're basically unleashing, it's like the climate is a spring-bound system, and we're releasing the spring, and
I mean, I recently saw an article, Paul. In fact, today I was just reading an article about northern Russia, and about how during the winter, the people up there have been noticing that, you know, while they have permafrost during the winter, they only have to go down a foot or so, and it's all slushy. And it never used to be like that before. So
Yeah.
we really need to melt that top bit, and then all winter we've got permafrost and methane and carbon dioxide coming up. So
Yes, yes,
let's talk to
exactly.
that.
Yes. See, okay, so it's estimated that the amount of methane that could be released from that's up in the Arctic on the continental shelves and things is, or I think it's just on the permafrost on the land. It's something like 1,700 gigatons. Okay, if a 0.3% of that was released, okay, that would be 0.3% of 1,700 is 5.1 gigatons. Okay, if that much is released, well, it turns out that there's only 5.1 gigatons of methane in the atmosphere right now, or actually the equivalence is to 1,700 parts per billion. So the 1,700 parts per billion global, when the global average was that, it's a bit higher now, that's 5.1 gigatons of methane.
Mm-hmm.
So what it's saying is, what I'm saying basically is if a very, very small fraction of the organic matter thaws and decays and produces methane, 0.3%, then that will double the atmospheric levels of methane. Okay,
Right.
so this is so this is what we're looking at. This is a huge.
I mean, just given the vast stores that we know of methane hydrate that are stored in the East Siberian Sea and in the Laptev Sea and so forth, and given all the great heating that's going in, I think it would be very easy for us to double the atmospheric load of methane with methane emissions. I mean, I don't see it not happening, to be honest.